In this session, we're going to talk about the normal approximation to binomial distribution. So, as you see, we're going to use a continuous distribution approximation to a discrete distribution, particularly binomial distribution. Why are we doing this? Let's try to figure out together. All right. So, if you remember the binomial distribution, we have trials, right? And trials for the observation of x events or cases. Okay, x cases. This is what we're doing, what we're dealing with. Okay, the number of heads in 10 coin tosses or something like this. Okay, so for example, suppose that you have 1000 trials for a particular event. So your x can take values from 0, 1, 2 to 1000, right? These are all the probabilities that could be calculated. But here it's obvious that direct calculation is not feasible, you see, because of the coefficients, right? If you have 1000 trials here, just think about the binomial coefficients that you're going to deal with. We can see this a bit about this more in the examples as well. But due to our central limit theorem, means that you have for high numbers of n for the trials. Okay, you will have lots of trials here. Your mu can be depicted with n times p, and your sigma square is represented with this one. I think you remember this from Poisson distribution as well. Okay, let's take a look at an example to understand what we're talking about here, about the approach. So your x variable shows binomial distribution with n equals 10 and probability equals 0.5. All right. So let's calculate the parameters now. Your mu is expected value as well. It's 10 times 0.5. That would give you 5. And your variance will be NPQ, namely it will be 10 times 0.5 times 0.5, which will give you 2.5, and your sigma would be square root of 2.5. It is 1.58. all right. Now the for x equals 3, 2, 3, and 4, let's calculate the probability here for x equals 2, 3, and 4. Even for low n, which is your 10. The thing is, when you try to calculate this one with the binomial approach, it would look like this. All right, this is for 2, 5 over 2 times 0.5 to the power 8 plus, these are your coefficients, or you are going to use the calculator. All right, 0.7 plus again and 0.5 over 4 times 0.5 over 6, right? This is how you're going to calculate this result, and the result will be power 10 times this much, and your result will be, I have already made some calculations, but you double check them yourself, and the result will be this one. All right. But if you want to make an approximation here, what can you do about it? Approximation here, right here, you see that your 5 is right here, your 2 is right here, your 3 is right here. All right. What is being asked to us is the probability of x equals this one. That's the thing that we're trying to calculate. So this is the area that we're trying to calculate right here, right? Okay. So, but what if I take these particular points and calculate the area under this curve part, right? If I calculate the area around this curve part in the normal distribution, I will get approximately the same value. Okay, there are some minor misses here, as you see. These parts will be maybe missed. Okay, I missed this part, I missed this part, I missed this part, and this one is also another mistake, and another mistake, and another. But who cares? Let's see if they compensate each other. Okay, and let's try to calculate the area under this curve from where to where? From 1.5 to 4.5. You see this from the histograms from chapter 1. You can see that this is clear. From 1.5 to 4.5. Go ahead and calculate the area under that curve. So this is what we have here. This one is 5, and what you're dealing with here is from 1.5 to 4.5 here, and we're trying to calculate the area under this curve. So that means that if you consider this as A2, and if you consider this as A1, area 1, namely this area, and namely this area here, the blue part would be what? A2 minus A1. See, the blue part will be A2 minus A1. Hopefully, let's see. So your x1 is 1.5 and x2 is 4.5. Your z1 is, let's make the transformation here, and it would be 1.5 minus, I know that my mean is 5 coming from the population parameters, and your sigma was what? It is 1.58. I have this, and the result would be minus 2.22. All right, and if I calculate this for z2 now, x2 minus mu over sigma, which would be 4.5 minus 5. Okay, I couldn't write 4.5 here. 4.5, okay, much better. Over 1.58, it would be what? Already calculated for you, minus 32 right here. But we need to have the corresponding areas or corresponding probabilities here. Let's take a look at 2. Again, we will rely on our table. 2.2 is this one, which is 48, 40, oops, not 2.22, right? I need to look for 2.22. Okay, I'm sorry. 2.22 is like this one. Okay, I made another mistake here, right here. You see, it is 2, not 2.2. So I need to go for 2.2. So you just be careful, okay? Don't make mistakes like me. Okay, 2.2. I hope I did this correct now. Okay, this one, right? Okay, it's 48.4860 corresponding area value here. P1 is okay, these are maybe confusing for you because I call this Z1 and Z2. A1, A2, and write this one as 1, A2. Okay, I think it's much better now. Your P1 was what? 0.4868. All right, this is your green area or green probability, and the other one is 0.32. So your 0.32 is this one, hopefully 0.1255, and this is your P2 is 0.1255, and your result will be okay. This one will be the probability of being from 2.2 to Z minus 2 would be P1 minus P2. So it would be, when you subtract them, that would be 0.3613. All right, this is your answer, and this is the answer to this question as well. Okay, the original answer was this one, 0.3662, and your approximation to this result is 0.3613. You see that these parts are exactly the same, up to 2-digit sensitivity here. Is it luck? No. As you see how useful it is, but the calculation with the second method is much more easier than the first one. I hope you agree with me that the second one is much more convenient to calculate. Let's just solve another example to make things more clear, hopefully. So about the normal approach. Suppose that a chemical production factory, a factory that produces some chemicals, chemical production safety in a factory is taken into consideration, and the safety of production is 98%. Okay, this is your safety. So if you produce each of the probability, independent probability of a particular product to be let's say working or to be acceptable is 98%. This is what we're talking about, and 1,000 samples taken are from that factory, like a set or something, 1,000 set here. What is the probability that X equals more than or equal to 27 defectives here? As you see that this is a binomial distribution, right? Because it's rather yes or no, or broken or functioning, or defective or not probability here. Now let's find the probability of defective here. One probability of defective here is 1 minus, it is 0.2. Probability is your p, and your mu is np, which is your, if you have a set of 10,000, 2 would be 20, and your sigma would be square root of npq here, which corresponds to 1000 times 0.2 times 0.98. That would give you 4 with this much of standard deviation. All right, so what is the probability of x is equal to or greater than 27? Let's calculate it with the binomial approach first. Okay, it is something like this, right? Probability of having 27 plus probability of having 28. Are we done? No. Probability of having 29 up to probability of having 1000 defectives, right? Are you crazy? That can be an easier solution, right? How about this one? Equal to 1 minus probability of having 0 minus probability of having 1 minus probability of having only 2 minus up to probability of having 26. This is much more easier to calculate, right? Are you crazy? This isn't easy as well. Now, as you see that we have to use normal approach to get rid of or to solve this problem, right? So let's do something here. So since you're expecting mu around 20 here, what you will have here is something like this. So what you're trying to calculate here is mu is 20, and you're trying to calculate something more than 27 here, right? More than 27, and you're trying to calculate this area, this particular area, right? 27 is also included, right? Greater than equal to. So I'm trying to calculate this area, this particular area. All right, wonderful. So, but what is this point right here? It is 29.5, right? This is what I'm trying to calculate. Wonderful. And this is your symmetry point, symmetry line. And your z, I need a z transform. For what? For why? Why I'm doing this for z transform? Just think about it. Because I want to use this lovely table. That's why I'm doing transform here. X minus mu, x minus mu over sigma. 26.5 minus 20, your population average, over your population standard deviation. It would give you this one, and the result would be 1.47. All right. So, but if I use the table, 1.47 will give me this area. Not the green one. So what I need to do is subtract this area to get this green area. Is that right? Please double check yourself. I think yes. And let's go ahead, use the table for this purpose. What's the number? It's 1.47, right? 1.40 is right here, and your 7 digit is right here. 1.47 is 0.4292. 0.4292. So your this yellow area is 0.4292. But what I'm looking for is greater than this one. X greater than this one will give you its probability of Z being more than this one, and the result will be 0.5 minus this value, 0.4292, and your answer will be 0.0708, and it would correspond to about 7% probability, right? This is what I'm looking for. 7% probability is the probability right here, and it is the probability that has been asked in the original question here, like point okay, it's approximately 7% is the answer to your question, right? Okay, let's just solve another example about the normal distribution to make a promotion for our next chapter as well. And I think this is a rather popular example, although it's an old example taken from the textbook. This is an example about a flu vaccine. All right, so God help us. Okay, now 100 people are injected with this new flu vaccine, and 68 people are not infected within that group, are not infected. The prior study shows that if no vaccination is done, if there is no injection, probability of diseases, particular diseases, God forbid, I hope it's not a very bad disease, it is 50% for a normal person. What can be said about the effectivity of this new flu vaccine? What can you say about effectiveness? What can you say about effectiveness of this vaccine? Is it effective? Does that give you any idea? So the prior was 0.5, and now this new probability is 0.68, right? The larger the difference, the more effective the vaccine is. That would give you idea. But how much is a good idea, or how much is does correspond to a good vaccine, or is it just luck? Now you can comment on it by how many standard deviations you are away from the mean. Okay, let's calculate this. So your mu is NP. This is 0.5. Give you are expecting normally 50 people of this 100 set should be infected, but it's not like that. It's 68, right? But okay, let's go ahead and calculate the population parameters. Okay, it's 0.5 times 0.5. This is the standard deviation you're expecting, and your x is 68. And let's make the transformation to understand where we are located in the standard normal distribution table over 5. That would give you 18 over 5, and it would give you 3.6. No, we're 3.6 away from mu, right? We are we are 3.6 away, sigma away from mu. So what is the chance for this one to be 3.6 away from the mean here? Let's look at our table. 3.6. I have here only 3.0 here. I cannot have 3.6 here. If you want to have 3.6 here, it should be something right here or something like this, okay? 3.6, right? But it's not in this table. But I can comfortably say that what is the maximum amount you can have here? 3.09, right? This is the maximum amount, and the probability of this one is this one. Okay. So it's at a very, very low probability, right? We're talking about a very, very low probability here. Okay, if you look at put 0 here, you put here 3.09, and this is our value 3.6 here, and we're talking about the area under this tail, right tail here. But up to here is, we know that it is 0.999. So this part would be up to infinity, of course. It would be 0.001, this green one. But how about this one? How about this one, the yellow area right here? It is much less than 0.001 percent, 0.001 probability right here. So much less than this, okay? So you can either say that, okay, they were really lucky with this 100 people. You can conclude like this, or you can say that there's something here. Maybe this vaccine is helping something. People are getting less sick here. Okay, how can we make the distinction here? Where can we draw the line? Where can we say that if a vaccine is effective or not? We can comment on this, right, using our objective statistical methods here, and we will use hypothesis testing for this purpose. So it's like an advertisement for this question, is particularly an advertisement for our next chapter that we will talk about hypothesis testing in our upcoming lectures, hopefully. Okay, thank you for listening.